Okay, so I've had a couple questions about the greenhouse effect FET lab, and I'd like to kind of clarify those because this is a really great simulation, and it will help us as we start to talk about our climate change unit. So this is an older FET, and it wasn't available to us because it was in Java still, but now it's become a legacy FET, and we can see it. You will be clicking on the link to play in the simulation. Here is the questions that you're going to answer, and I will go through those with you. Dr. Bozeman is fantastic, but some of you said that his video didn't quite answer the questions that you were looking for. So let's go ahead and look at the questions that we have. First question, which kinds of photons are absorbed and re-emitted by atmospheric greenhouse gases? Which kinds of photons are absorbed by Earth? Which kinds of photons are emitted by Earth? So when we're talking about photons, we're talking about these photons here. We're talking about energy. We're talking about like photons of light. Okay, there's also in this simulation photons of infrared, so which is also on the light spectrum. But let's go into the simulation. And the first questions ask us about photon absorption. So let's try to go to the photon absorption tab. There we go. And we can see this is a molecule of methane, which is CH4. That is an atmospheric gas. And we're going to go ahead and put some infrared photons on this methane. Looks like methane did absorb some infrared. It bounced off some infrared, and some infrared went right by it. And then we'll add visible photon, or change to visible photons. The visible photons are not affecting the CH4, just the infrared. So that heat of the infrared affects the methane molecule. All right, let's go to CO2. CO2 is not affected by light. Is CO2 affected by infrared, by heat? Oh, look, it starts to bend, kind of dance, it looks like. And that, taking in that energy causes the molecule to deflect or move the energy. Not all of it is passing by. Some of it is reflecting back. All right, let's look at water. Water is an atmospheric gas. It does bounce back. Some of the heat, it does bounce. And some of the heat still goes by and goes through. Let's look at visible light. No effect on water. All right. N2, visible light does not seem to affect the nitrogen gas. Look at the heat, the infrared photons. Let's give it a second, because the other ones took just a little bit of time. It does not appear. Nitrogen gas is not affected by the infrared nor the visible light. Oxygen does not seem to be affected by the infrared. Let's check the visible light. Not affected. So when we go back to those questions for this first, which kinds of photons are absorbed and re-emitted by atmospheric greenhouse gases? So we go back to that thing about that simulation. CH4, CO2, they both bounced back. Even water bounced back some of the infrared. So that would be the re-emitting the infrared. So those three molecules are what you want to put for the first question here. And then, so first question, which kinds of photons are absorbed and re-emitted by atmospheric greenhouse gases? Read that again. The kinds of photons was infrared. Visible light was not affected by the photons, or did not affect the gases at all. Which kinds of photons are absorbed by the Earth? Okay, so we're talking about infrared photons. Which kinds of photons are absorbed by the Earth? Well, we'll need to go back to our simulation. And let's go back to the Earth part. And we'll let them flow. Here are, so you can see some visible light, some sunlight photons. We're not seeing any infrared photons yet, but let's go ahead and hit play and see what we see. It looks like if we watch them fall, the visible light are absorbed by the Earth, and then infrared comes out of the Earth is what it appears to be doing. I don't see any infrared up here in the top coming down from the atmosphere, but the infrared, these red particles, are rising from the Earth. So that means that the sunlight is warming up the Earth. Okay, so let's go back to our question. Which kinds of photons are absorbed by Earth? The visible light photons, the sunlight photons are absorbed by the Earth. Which kinds of photons are emitted by the Earth? We can see that in the simulation. These red infrared particles, photons, they're not molecules, they're photons of energy, but they are coming out of the Earth. Okay, so the infrared are being emitted by the Earth. All right, let's look at our next question. What effects do clouds on the visible light photons coming from the sun? Or what effects do clouds have on the visible light photons coming from the sun? Does this have the effect of cooling or warming the Earth? Explain. Well, we need some clouds, don't we? Let's see. All right. So adjustable concentration. Looks like we do not have a cloud. Oh, number of clouds right here. Options. Let's put tons of clouds. That's all we can put. It's 3. Okay. So we have 3 clouds. Let's watch what happens with our clouds. The sunlight does not reach to the Earth. There's still infrared under the cloud, but it seems like the infrared went through the cloud. Let's watch over here. There's lots of infrared over these houses. It seems like this infrared is not, there's a few passing through, but a lot of this infrared is kept on the surface. Let's take it down a cloud so we have a little empty space and compare these 2 areas. Go ahead and reset. Let's reset it to get a real clear view. Okay, so we're going to go with 2 clouds. So we have one of these building areas covered and one of them not covered. And we're going to go ahead and watch what happens. Okay, so sunlight is coming down from the atmosphere or from space, from the sun. It hits the Earth. It is absorbed by the Earth, and infrared is coming out of the Earth. And let's watch those clouds, particularly that cloud layer. Notice that. Now we have some of the infrared is coming back to the Earth. Whereas over here, the infrared just rises. So it appears that the clouds create a blanket. The clouds hold some of the heat next to the Earth. That's an interesting thought when we think about clouds of pollution. Keep that one in your head for a little while. But let's go back to our questions. What effects do clouds have on visible light photons coming from the sun? So the light couldn't come in to the Earth. Does this have an effect of cooling or warming the Earth? Explain. Well, if the light can't get to the Earth, it can't warm up the Earth. What effects do clouds have on infrared photons coming from Earth? Does this have an effect on cooling or warming? Well, it appeared that the clouds created a blanket, and the clouds were keeping that infrared in. So how do you think that would affect our Earth? The sunlight can't get to the surface, but the infrared isn't leaving. Okay. Think through that one. Okay, compare the atmospheric simulations The Ice Age, 1750, and today. What is the equilibrium temperature of each time period? You may use whatever units of temperature you like. We can stay in Fahrenheit if you want. I know the rest of the world uses Celsius, but we're Americans. We got Fahrenheit down in our head. So we'll just, whatever you would like to use, but I'm going to stick with Fahrenheit for our simulation. We can see today, we're already on today in the atmosphere. We have some clouds we can take away, we would like. And that equilibrium temperature is kind of staying right at 42, 43. Kind of creeping up a little without, let's see. All right. So it kind of hangs out right around 40, 48, 49. See, it's bouncing back between 49 and 50. Yeah, around 50 degrees Fahrenheit is probably the right answer. Let's look at 1750. Okay, so 1750. Let's reset it. I feel like we got some of that infrared still in our system. Okay. We'll kind of watch it. Sunlight coming to the earth. What effect is that going to have on the earth? It's going to warm the earth. The earth is going to take in that sunlight. All right. Notice how it's rising pretty steadily. We're not hanging out at any temperature. See what we kind of stalling out there at 35, 36. $43, $44, $43, and then $45, $46. Okay, so it's kind of hanging out right there at 46, 47, 48 degrees Fahrenheit. And remember, that's like the average. So there's really cold places, really hot places. So the average we'll put at about 47. Let's go ahead and reset that. We'll let it continue at Ice Age settings. And then we'll answer our question. So today it was about 57, 1750. It was about 48. Okay, let's look at what the Ice Age is doing. Ice Age. Okay, I have some sunlight coming into the picture. I'm glad we have that setting on fast. Woo! Notice the difference in the Ice Age landscape. All it is dirt and snow. Whereas in the today, in the 1750, there was grass, there was buildings, there was other things. So it's important to kind of recognize those do have an effect on temperature and the way the photons are absorbed or re-emitted. We're rising way slower. Kind of hanging out there for a second at 12. Going to 17, 18, 17, 18. All right, so we're kind of bouncing, kind of hanging out right there around 25. So let's go ahead and put that in our answer. There's 25 right there. That's a big difference. All right, what are the concentrations of the three persistent greenhouse gases, carbon dioxide, methane, and nitrous oxide for each time period? So we need to go back and look at those. And well, we'll just wait to reset it. But right here, this greenhouse gas composition, that's what you're going to write down. So for the ice age, since we're already here, CO2 is at 180. Methane was at 0.380. And nitric oxide was at 0.215. All right, let's look at 1750. So we'll come back up in history. Now, ice age CO2 was at 180. In 1750, it's at 280. That's a significant, interesting piece of information, and we're going to look specifically at that one for today. CH4 is at 0.73, and nitric oxide is at 0.270. So all of them have increased, almost doubled, almost. And then today, let's look. Let's make sure we had our numbers right in our head. Ice age was 180 carbon dioxide. Okay. Today, 388. So we have more than 200 parts per million more CO2 than the ice age had. And then CH4, we have 1.84, whereas before we hadn't gotten over 1 part per million. And then nitric oxide has also risen, not quite to the same ratio, but it's interesting to see how the carbon dioxide has increased. So kind of beginning to think about, if carbon dioxide continues to increase in the atmosphere, what does that do to that average daily temperature? As we saw with the average daily temperature and the exercise we just did, today is a lot warmer than the ice age. Now, are there other factors? Probably, but questions to ponder, building your thinking, building your thoughts on these things. Okay, what is the relationship between equilibrium temperature and the greenhouse concentration? So you need to draw out that relationship. Simulate the Earth if its atmosphere were completely stripped. What equilibrium temperature would we have? Okay, so completely stripped, what would that mean? Well, let's say there was none. We're going to move the greenhouse gas concentration to none and see what happens. So like, we still have the buildings of today, and we still have the grass and stuff of today. But what happens if we have no atmosphere? And that's what we did here. We took away everything. What do you notice? Look at that temperature, the average daily temperature here continues to drop. Okay. Sunlight is coming in, but heat is just leaving. It's not staying. I guess that's something that we should really point out too. We look at today with the higher CO2 concentration. Kind of watch. We can kind of see where they've illustrated our atmosphere might settle in at. As we look at, we're in the today setting, so watch see those infrared photons. They kind of get bounced back, some of them leave. That's true, we lose some heat, but you notice right here, we're keeping them. We're keeping the heat at a lot more higher concentration than what was actually leaving without the greenhouse gases. So we need that atmosphere. We need greenhouse gases, but we need to consider those as we can kind of move forward in our own thinking. Okay, so here is a specious argument. According to the simulation, the average temperature of the Earth with the maximum concentration of greenhouse gases is only 10 degrees Fahrenheit warmer than it is today. That's nothing to worry about. Explain one thing wrong with the statement. Now, you might have to do a little research for that one. But 10 degrees. Think about the difference between frozen water and liquid water. Think about when you drive. If it's 36 degrees, I'm probably okay. If it's 32 degrees or 31 degrees, I need to watch out for ice very carefully. And so you want to think about those kinds of things when you answer that question. Okay? All right, hopefully this video helps. I apologize for the confusion.